Hello, I'm Ovidiu G, but you can call me Ovi. This is a statement of comparability of UK Nordic, and it shows my two master's degree, one in electrical engineering design and the other one in industrial engineering design, which was mainly mechanical. Both of these master's degree specialized on CNC machinery. Now, the purpose of this tutorial is to serve as a reference for my CAD/CAM engineer CV, and also it serves as a personal purpose to test ideas combined with the work field I've served for the past 6 years, which is CNC machining, setting, operating, offline programming of CNCs. This is how the machine is going to look after our first two videos. It is a 3-axis horizontal paired with a twin spindle with a sliding spindle on the left. We are taking things slow in the first video because we are still refining. The design of the 3-axis horizontal CNC, but we are speeding things up in the second video where we're simulating the bolt assemblies, the welding assemblies, and we're also drafting the sub-assemblies and components all the way to explaining how they're going to be manufactured on CNCs and generating numerical command codes and explaining those as well. So I hope you enjoyed this video. As you can see, I've changed the color of all of the components in order to help me explain their purpose better. I'm not going to focus on the way we can use solid edge CAD software as much as I'm going to focus on steps and methods of using a CAD software in general and the possibilities that it offers. For example, we've just modeled and assembled this already, and we can do this in any acceptable CAD software. What we're going to do from now on is going to take the values of the materials that we've assigned to the 3D models and assembly, and we're going to start applying forces. I'm going to show you here. So we're going to start applying structural loads, constraints. We're going to connect the faces, we're going to mesh it, and then we're going to solve it just to see if the stepper engine and servo engine we find online and their nominal values can be inputted in a CAD software, and we can simulate how the machine's going to work and perform in work environment conditions. As we go through the components, I'm going to explain the color code. So white is for aluminium, gray is for cast iron, red is for the electrical stepper engines and servo motors, yellow is for the spherical profiled thread, and blue is for the linear bearings. Now, aluminium serves as fixed mounting position for the other elements of the assembly. The cast iron is supposed to take some of the structural load from the linear bearings, and it's also supposed to prevent small bendings and twists that happen over time, normally in metal. As a designer, I should know. This CNC machine is going to be within a 0.001 to 0.01 tolerance. Small bends over time are not accepted. Now, the spherical profiled thread is supposed to convert the rotation from the stepper engine into motion of the rails, and the linear bearings are supposed to take that motion into a almost perfect straight line. As we can see, two linear bearings and two straight lines are going to form a plane. So we have a 90-degree plane of the x-axis to the z-axis, also a 90-degree from the z-axis here to the y-axis. Because the linear bearings, the spherical thread the stepper engines are going to be ordered, I'm going to focus my attention on the connecting elements that have to not only satisfy the geometrical condition I've explained earlier, also has to satisfy the power necessities of the engine so that they efficiently transfer the power of the engine all the way to the cutting material, resulting the swarf. Okay, so the total power of the equipment is going to be 1 kilowatts. This is only half of it. So that 1 kilowatt is going to be divided between 6 stepper engines and 2 servo spindles, even though it's going to have 3 servo spindles, but they're not all going to work at the same time. As in terms of force, I'm going to look for the linear bearings catalog and see the power transfer per rail to cage multiplied by 4 and calculate the force that can be transferred between the moving elements. Okay, so looking at the catalog of the rails, we're going to have to choose between HG50 and HG20H. So we're going to have a static moment between 100 and 350 Newton meters, or a load rating of 16.9, that's 17,000 newtons, all the way to 36,000 newtons. Just to make a comparison, this is about 16,000 newtons is about 1.6 tons hanging due to gravity force. Just the same 36,000 newtons is 3.6 tons hanging due to gravity force. So it looks like we'll be simulating between 16,000 newtons and 36,000 newtons. I think we have enough information for now to simulate the first forces that are going to act on this assembly. Now, just to show you, this assembly has already gone through some refinements. This is the block between the x-axis and the z-axis, and I gave this block up because it didn't provide enough transfer from this surface of contact to the surface in between to the x-axis. Now we know that these linear bearings are going to transfer 35,000 newtons per cage, and we're going to simulate on this block that's going to be fixed to a concrete plate the surface of this cage on the rail on the z direction with 35,000 newtons. Now, why the z direction? Normally we would simulate the x, the y as well, but we can easily see that on the z direction would be actually the direction of which the gauges are going to be pressed on the rails, because any force applied to the spindle is going to be rotating the vertical block, which will translate into pressure applied on the rails in the z direction, z plus or z minus. Now we're going to simulate that force being transferred to the material. We have to keep in mind that finite element analysis, or FEA, is an approximation method, so it's going to approximate the best values, but with confidence I can say that most designers use this to back up their design with stress tests and so on. So we're going to start a simulation with new study. We're going to leave it at linear static, and we're interested in the displacement and the stress because of the bending and the braking. So we're going to hit OK. We're going to leave it at that. We're still refining. It's asking us to select the elements that are going to be involved in the calculation, just like that. Now, as I'm sure you remember I've mentioned that the back is going to be fixed on concrete-like structure, so that's going to be fixed in this calculation, and hit enter. Now we need to apply the load, the 35,000 on this surface. And this other one I'm going to select through the material. The force is going to be a vector composite in the Z direction of 35,000. Hit enter. Now we have to connect the faces. This is done automatic. We hit auto on connectors. The software is going to propose some connections. I trust the software. It's sticking the faces together as if they're glued, and it's good enough for this level of calculating. And now we have to apply the mesh. I want it to show me the mesh, and I'm going to leave it at coarse. We're going to wait on the result. Now that it has calculated the mesh, all we have to do is hit the solve button and wait for the results. And this is what the simulation results look like. As you can see, it's shading some faces here. I don't know why. But if we click on the right here, the stress in the material by factor safety starts from 2000. So you got a 2000 factor of safety all the way in the red area, so that one's not going to break. And again, we're looking at a total displacement of 1 millionth, so it's e to the power of 6. So it's safe to say that this assembly, it's going to take the 35,000 Newton per cage, and we're going to estimate that it's going to take the 140 in total, and the best direction of that force to be applied would be on the Z direction of the vertical block when it's moving sideways. So it passes this test. We're going to create a report with the create report option, and this is a simulation of all the 4 cages being pulled by 4 times the force, and that's 140,000 newtons. As we can see, the total displacement is still within 1 by the power of -5, so that's more than microns. And the stress for the factor of safety is still over 2000, so the simulation passes also. Okay, so we're back at our assembly. I can see that by moving the components, some of it is mixed up. That's okay. I was just about to show you how we've simulated the fixed component and the force of the first moving component. Here we have everything we've added. Now we're going to simulate the vertical component, and I want to say that in order to have the force applied at the bottom, there's going to be a force applied at the top. So we're going to do the ratio of bottom to height. That's around 2.6, and out of 140,000, it's roughly 52 something. So I'm gonna simulate for 55,000 newtons on 4 cages, on the y direction just to simulate that sideway movement I was telling you about. That's going to put the 35,000 per cage. So again, here we have the vertical block. The bottom's going to be fixed, and the top here on the same surface I've showed before, on the same surfaces that I've showed before, we're going to apply the forces. So new study, leave everything as it is, select the components, hit enter, select the fixed faces, hit enter. Now select the load faces, I'm going to select these faces. Okay, now that I've selected all the faces, we're going to apply a vector composite of 55,000 on the y direction. And we have defined the load as well. Now we're going to connect the faces. We're going to accept those connections. I want to show you something that simulating this before, I thought that these faces sticking together are going to add too much resistance. So I lifted them up just so we're simulating only the aluminum base. Now we're going to select the meshing, leave it as it is, wait for it to solve. The meshing's done. We are going to select the solve button and wait for the results. These are the results. We're going to look at the factor of safety first. It's about 171, so that's pretty close, or not, it depends, I guess. And the total displacement is still 0.3008, so I'd say that it's acceptable. So now that the second component has passed the test, we're going to look back at the assembly and go for the third component. So what I've done so far was try to fit my assembly to the linear bearing readings. So far we've managed to simulate the first and the second block. Now we're going to simulate the third block. If you remember, we've done a reduction from 140,000 to 55,000. That's because of the base to height ratio of applying force. We're not going to do one for the third component. Seems this one's going to be acting pretty close, the load on this side to the fixed faces on this side. So we're going to apply 55,000 on this third component. Now this block here is going to be fixed on the Z cages, and it's going to be pulled by the cages from the Y direction. So this is the Z and this is the Y. And again, we're going to hit new study, leave everything as it is. We're just estimating. We're going to apply the fixed Now we're going to apply the force of 55,000. We're going to apply the connections and the mesh. And we're going to hit solve. Calculations done. We're going to look at the safety factor. That's 265, so it's a bit more than the second block, which was 171. And we're going to look at displacement, a total of not even 1 micron, so it's still good. In fact, these readings are so good that I think I'm going to modify this whole block to a single plate because of manufacturing reasons. It's probably going to cost me more to cut all these blocks and assemble them together, so a thicker plate should cut it at this point. I didn't think it would go this good, so let's find a plate and simulate it as if we wouldn't have to assemble everything like this together. Okay, so this would be the plate in between. We're going to switch the material from aluminium to cast iron. Yeah, like I've applied all my cast over the model. So I'm going to switch from that whole assembly to just a plain cast iron plate, simulate it, and see if it's good enough. Leave everything as it is. Define the elements, defined, fixed on this side, force on this side of 55,000. Now there's no connecting elements, so we're going to mesh it. Should happen faster, and solve this calculation of the 55,000 newtons applied directly to a cast iron plate. And this is actually good news. My safety factor jumped from 260 something all the way to 2,000. So that is not bad at all. This is going to simplify the model a lot. And displacement, make it good, still under 1 micron. So yeah, we just simplified this model. Okay, so we're going to close the simulation and go back to the model. Now, coming back at the model, we're going to continue simulating the force from a 55,000 on a fixed position on the machine on this block, the third one, all the way to the fourth block, and again we're going to apply a fixed on the back here, and we're going to do the same transformation of base to height ratio from the back all the way up to the front to determine the force that applied here at the front is gonna add up to 55,000 here at the back and all the way to 140,000 at the base. Now the ratio should be around 3 from 55. That's almost 20. I'm going to go with 20,000 newtons here on the tip. So here we have the fourth block of the assembly. New study. Leave things as they are. select geometry, select the fixed, and this time it's gonna be all of these faces. Now we've selected all the faces for the fixed. We're going to apply the force right here on the spindle of 20,000 newtons. We're going to connect the faces. And mesh. Now with the meshing done, we're going to solve this calculation. And these are the results. We're going to look at the factor safety, which is 414. That's good. It's close. Still good. And a total displacement of 2 microns. So this is where we're hitting the limit. In order to maintain the equipment within tolerance, I can see we're hitting the tolerance on the tip here. But if we think about, we're applying 2 tons as if they were hanging due to gravity. So for such a small equipment, I'd say it's good enough. So this component has passed the simulation as well. Okay, so to understand what we've done so far, we've simulated the maximum power transfer of the rails between the components, and we've done this by starting off with the highest force on the fixed element to the lowest force on the last moving element. We can safely say that this machine can withstand a 2000 Newton force on the top of the spindle, and we can say this in such few simulations because every time we have simulated, we went for the weakest point of the machine. So if you look here, the vertical block moving sideways is the weakest ratio of base to height. If it can take 55,000 on the y direction, it can easily take on the x direction as well. Same thing applies to the fourth component. If it can take on the x direction 20,000 newtons, it can very well take them on the z direction as well. If you remembered a while ago, I said that this modeling has already went through some refinement when I was eyeballing it, the component. Now it's gone through a second refinement. So what I've learned so far is that this third block here is going to be changed with a plate. It's going to be easier to manufacture. I also don't like some things here, how they waste some spaces. The second thing I've noticed is that the twisting elements, these are supposed to prevent the fourth block from twisting, so I'm going to make them longer to provide more resistance on the fourth block. Okay, so we've made the modifications to the model. In short, we've lengthened this from 1000 to 1100. We've also modified the rails and the cages of the linear bearings to the descriptions from the catalog of the 20 wide rails that we've simulated for the 35,000 tons, and for the x direction and the z direction, and we've simulated the 15 wide rails of 16,000 newtons per cage. So we've got two types of rails on the X on the Z1 type and the second type on the Y axis. We've also, due to simulation, we've noticed that the Y block, this one, was also too complicated, and we've opted for something simple because it could withstand the force transfer from the blocks it was connected to. So this one's smoother. I like it better now. It's smoother. I haven't changed this, and I'm gonna change it in a bit, and then we're going to simulate if the machine can withstand 20,000 newtons on the tip of the spindle through the whole assembly all the way to the base plate. Okay, now that looks better. Now I'm gonna hide all the components like the engines, the spherical thread, and so on that we don't need for the simulation. So now that we've cleaned this up a bit, let's see what the simulation says. So same thing, new study. I'm just gonna check to make sure I have the materials applied. Yes, everything's in place. We're going to do some fast computing first. Select it all. Apply the fixed constraint. Apply the force of 20,000. In the Y direction. This direction being the most sensible, but we're going to test the other directions also. Okay, so we've applied constraint connection. We're going to do the connections. We're still keeping it simple. This one's gonna hurt my PC a bit. It's already slowing down a lot. I'm gonna slow it even more. Let's wait for the mesh now. I see that I've gotten pretty far. I've managed to mesh the whole assembly. I'm going to hit solve and we're going to wait for it to solve. As you can see, we've gotten an error. It was so expected. We've simulated this in a bit of a rush. I'm going to take a look at this and make sure this simulation is still possible. Okay, so I see that it can go without the base plate. I'm gonna try to get the base plate in also. If I can't, I'm gonna take a look at the safety factor, which is 76. It's pretty good considering we're applying 2 tons. And the displacement, this one's the important one, is of just 6 microns. So if we apply 6 ton on the spindle, it's gonna be displaced only 6 microns. Okay, so we couldn't simulate the assembly with the base So we went along and simulate without the base. Now we've simulated the 20,000 in the Z direction. As you can see, the factor of safety is 271 and the displacement is 4 microns. Okay, so it's safe to say that the model has passed the stress test, the initial stress test. This model has gone through some filtering when I was modeling it, and now it has gone through the second filter of passing the stress test analysis. Okay, and as a conclusion, a designer should know the force and the rate at which force gets transmitted, also the material resistance in Newton per meter square pressure that you can apply into the thickness of the model. So mainly the simulation has shown that I've estimated correctly the resistance of the model. Also for a weekend job, because all this has been done into one weekend, I wouldn't say it's much, I wouldn't say it's nothing. I've managed to model, assemble and stress test a initial stress test of the assembly to make sure that we can achieve a 1 to 10 microns tolerance into a 800 wide, 420 long and 420 tall work environment in which we can apply a 20,000 Newton force. So what's going to happen now is that I'm going to order the components online, double check their dimensions, then put those dimensions into my model and simulate it at a much finer course to see if I can make some real improvements. If not, only then the components are going to be passed on into production. So we have to wait on the linear bearings, the engines, and spherical thread in order to confirm those dimensions and put them into assembly. I know this as a fact. It's good to double check your dimensions before you order the manufacturing of the components. Now this is the sort of work I would do as a CAD/CAM engineer at the prototype department, and while I was just assistant engineer on the conceive and the design process, when the components would be verified and approved for manufacturing, I would be the senior engineer in designing the manufacturing process. Because this video is coming to a close, I hope you guys enjoyed it. I have something written down here. This video is going to come to a close, and in my next videos we're going to go through the steps of CAD designing and CAM manufacturing of our own CNC. So we are going to go through drafting for assemblies and parts so that the people from manufacturing can understand what we want with our 3D model. And we're going to follow the geometric conditions for the machine to work properly. We're going to do assembly drafting with specification of torque per screw in assembling the screws into the assembly. We're going to explain how the raw material is going to be assigned to a certain type of machine that is going to manufacture the part according to the condition that we have specified in the draft. I'm going to generate a command numeric code for a CNC machine just like the one we're designing, so we can go to the steps of utilizing a CAM software and better explain the functioning of a CNC. We are also going to take the 20,000 Newton force and other mechanical constraints, and we're going to transform them in characteristics for the stepper engines and the servo engines. We're going to simulate numerical filters as high pass, low pass, all pass filters that are necessary to modify the electrical geometry of the commands of the engines to better serve as a safety for certain feeds and speeds at which the machine is going to work on proper. So we're going to do that in our next videos. I hope you enjoyed this video. Have a great day and remember to have fun at work.